This is Math 156, Maple, Lecture 4. So let's start by looking at some geometrical problems. We have a parabola, x squared plus x minus 7, and a cubic, x cubed minus 10x plus 3. We want to plot them on the same graph and find the points of intersection. So I write the two functions, the two equations in curly brackets, and that's what the graph looks like. So we can see these curves intersect at 3 points. I want to find the 3 points. Let's say I want to find the points of intersection graphically and with the command fsolve. So let's just blow up the curves around these 3 points and get a better idea of what the coordinates of the point of intersection are. So, for example, this point is between -4 and -3. So let me graph this from -4 to -3. So I can see this point is really between -3.3 and -3.2. Let me just blow that up a little bit. I've blown it up some more. It looks like it's between minus, let's say, 3.29 and 3.27. Looks like it's a little bit bigger than 3.28 and maybe less than 3.283. Not sure. Closer to 3.282 and 3.281. Yeah. So here we have the point of intersection to 3 decimal digits. It's like minus 3.281 something, and the y is right up here. So we just found this point. What about the second point? It looks like it's very close to 1. So let's blow up our curve close to 1. Maybe from 0.9 to 1.1. Well, maybe 8.9 and maybe 9.1. Oops. That looks like it'll be a little bit closer. Here we are. So it looks just a little bit bigger than 0.9. Let me make this 0.9. Yeah. So it's really between 0.901 and 0.902, I think. Yeah. So like 0.29, 0.9017 maybe, and 0.9018. Oops, too much, maybe 19. Make this 18. Yeah. So this point of intersection, the second one right there, is about 0.9018. Yeah, that's pretty good. What about the third point? It's like a little bit bigger than 3, maybe between 3 and 3.5. So it looks like it's around 3.4. Well, a little bit less than 3.4. Maybe 3.37, 3.39. Yeah. very close to 3.38. Oops, no, a little bit less. Ah, I'm just making, all right, so there we are. So this point is 3.379 something. Oops, too much. Yeah. So 3.379, between 3 and 5. Oh, there we are. So that's the third point of intersection. So that's using the curve to solve this equation graphically. To solve it algebraically, if you like, we use the fsolve command. So one way to do this is to say, find the points x where this quadratic equals the cubic. Solve that equation for x, and we get three numbers. Yep, exactly the three that we found. So that's a nice way to solve this problem. Right? Okay. Let's recall how to define a function in Maple. So if you want the function x squared, it's not just writing x squared. Let's give it a name. Let's call it f of x. So it would be f colon equals x and then an arrow. You get an arrow by doing a minus sign followed by a greater than sign, x squared. So now we have a function. F of 0 is 0. F of 1 is 1, and so forth. If we want to make a loop to see what the first 10 squares are, you could say 4, oops, any letter we want to choose, k, from 1 to 10 do. I do shift enter to move the cursor down a line. I have to end this do loop. So this is how to set up a, it's called a do loop. For k from 1 to n do, and I have my n do there, and what I want to do is compute f of k. F of k is k squared. So this gives me the first 10 squares. I could write k comma, and then I'll just know that, for example, 5 squared is 25. I don't have to go from 1 to 10. I mean, I could go, I don't know, from 379 to anything I like, 385. And then here I have the numbers from 379 to 385, and they're squares. If I don't want every square, let me change this. Maybe this is, again, from 4,182 to 4,211. Oh, a lot of them. There they are. Each of these numbers on the left, and here's the square. Suppose I only want like every third one. I could say go up by threes. So I would put in by 3, and now I'm going up by 3. I start at 4182, and then plus 3, 85, 88, and so forth. Okay? This is just a little bit of practice using a loop. Remember, we have our function f. Oops, let's see. What is f of x? X squared. How do we find the derivative? You use the letter d if you're dealing with a function. So if I say d of f, that's the function, x goes to 2x. If I write d of f at x, that's derivative of x squared, it's 2x. Suppose we want to find the tangent line to the function f of x equal x squared at x equal to minus 3. So the tangent line, I'll call it tangent line, is equal to the derivative of the function at 3 times x minus 3 plus the value of the function at 3. So this is the tangent line, 6x minus 9. The way we found it was to use the point slope formula for a line. Suppose I want to plot the parabola and the tangent line together. I would say plot, and then together f of x and the tangent line. I wanted the tangent line at x equal minus 3, but I plugged in plus 3. So this should be minus 3, minus 3, and minus 3. Now that is the tangent line. Yep, and here it is. At x equals 3, that is the point of tangency. Recall that the normal line is the line perpendicular to the tangent line. And the product of the slopes of perpendicular lines is minus 1, unless one of them is horizontal and the other is vertical. So how do we find the normal line? Oops, I should have had this hashtag means just text. So what is the normal line for this function f of x equal x squared at x equal negative 3? So it's the negative reciprocal of the slope of the tangent line. That means the negative reciprocal of the derivative of f at minus 3 times x minus minus 3 is x plus 3 plus f of minus 3. So that's the normal line. And now if we go back, let's plot the tangent line and the normal line and the curve together. So the red is the parabola, the blue is the tangent, the green is the normal, but the green and the blue do not look perpendicular. And the reason is that this graph is not drawn to scale. 1 unit horizontally is much bigger than 1 unit vertically. So if I can manage to pick up this menu and I click on scaling constraint, now it is drawn to scale. Parabola goes up pretty fast. Let me just say x goes from minus 10 to 10, but y goes from minus 20 to 20. That's a little bit better. So now it's drawn to scale. The red is the parabola. Yeah. The red is the parabola. The blue is the tangent line, and the green is the normal line. Good. Suppose we want to plot something like plot the curve defined, let's say, implicitly by an equation like x squared minus 7xy minus y squared plus 13x equals 20. Oops. Okay. We want to make a remark in Maple. That means write down some text that's not treated as a Maple command. You just prefix what you write by this sharp sign above the 3. So we could maybe solve this equation for x or for y, but it'd be kind of messy and ugly. So there's a command that allows you to plot a curve implicitly. So far, the only plotting command we had was plot. But in fact, there are many different graphical ways to plot something in Maple. But you have to open up a package of plots. And the command to open up a package of commands in Maple is with. So if you write with plots, you have all of these different ways to graph things, to plot things. And most of them we'll never use in this course. But one which we will use right now is something called implicit plot. So the syntax is you write, first you have to open the plotting package. Then you say implicit plot. And what we want to plot is the curve defined by this equation, x squared minus 7 times x times y minus y squared plus 13 times x equal 20. And I have to give a range of values for x and y. Oops, it should be 7 times y squared. I think this is right. let's just see what happens. X goes from minus 10 to 10, and Y goes from minus 10 to 10. I have to give a range of values for both X and Y. So this seems to look like something like that. That's kind of interesting. Suppose I go a little bit further out. Yeah. Oops. This is what I want to change. Yeah. Looks like I have a hyperbola, but twisted. Very pretty. So this is a hyperbola. Oh. So this is the plot, implicit plot. By the way, when you give this command with plots, if you don't want to see all this stuff on the screen, if you end the command with a colon instead of a semicolon, it opens the package, but it doesn't clutter the screen with all the words. So I usually do that. I prefer that. Oh, that's another nice command. What are some other things in Maple that we haven't done yet? I tried to do some high school algebra, but let's do a little bit more. Factoring. So there are two kinds of things you do in high school. You might have a polynomial like x squared minus 5x minus 6, and you want to factor it. Well, the command to factor in Maple is easy. You just write the word factor and put the polynomial you want to factor in parentheses, and there it's factored. What if this were a cubic? Oh, that one doesn't factor, it seems. Let me change it. Ah, this one did factor. Yeah. Ooh, that's a surprise. This guy factors, though. Not so obvious that it does. Yeah. So if you want to factor a polynomial, the command is just to factor. Suppose you have two polynomials, like 2x cubed minus 7x plus 9, and you want to multiply that by another polynomial. Yeah. Well, nothing happened. Just doesn't multiply. But there's a command which I think works, which is expand. So to expand this, you put what you want to multiply together inside the parenthesis, Ah, there it is. It does multiply the polynomial. So the command to factor polynomials is factor. The command to multiply out polynomials is expand. Let's see. I'm curious. For n from 1 to 12 do, what happens if we factor the polynomial x to the n minus 1? Let me put an n comma so I know which we're doing. Ooh, look at that. This is x squared minus 1, x cubed. They're all divisible by x minus 1, but some of them have a lot of factors. Some of them just have one other factor. So here I use the loop for factoring. Right? Loop is a very versatile command. Suppose I want to factor an integer. Like 6 is 3 times 2. So if I say factor 6, it doesn't factor it, because factor is the command to factor a polynomial. If you want to factor an integer, there's a command I factor. That means integer factor. And if I factor 6, I get 2 times 3. If I factor, I don't know, 725, that's 5 squared times 29. Let me make it a bigger number. I'm sort of curious. Oh, look at that. So this number is 7,252,232. That's 2 times 2 times 3. And this is a prime number. A prime number is a number is an integer strictly greater than 1 that has no integer factors. There's an integer n that has no integer factors except the trivial ones, 1 and n. So this is a prime. And there's a command in Maple that tells you whether or not a number is prime. It's called isPrime. It's like asking a question. Is prime 3? True or false? True. 3 is prime. Is prime 28? False. 28 is not prime. Is prime this number? 604,361. True. Ah, so that really is a prime. So this is the factorization. Suppose you want to factor the first 100 integers. You could say for n from 1 to 100 do. And do. And what you want to do is I factor n. Oops. Why didn't I do it? Oh, I ended with a semicolon, a colon instead of a semicolon. There we are. Let me prefix this with an n so I know what n I'm factoring. Yeah. So like 87 is 3 times 29. 88 is 2 times 2 times 2 times 11. These are all the factorizations of the first 100 numbers. If you want to make it more challenging, I don't know, about from 10,043 to 10,089. Factor all those numbers. Yeah, took a second maybe, but we have 40, 7 numbers. This is their factorization. Suppose I want to know which of these numbers is prime. I could have said the following. For n from here to here is prime. So this will give me true or false. True if n is prime, false if n is not prime. What do we got? False, 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 false. One guy is, this is a prime, this is a prime, and this is a prime. So in this range, there were only 3 primes. Now, of course, half these numbers are even. So they're definitely not going to be prime. And we didn't have to look at the even numbers. I could have said, just look at the odd ones. Or let's go from here to here going up by 2s. I can write by 2. And then it just gives us, starting at 1043, it goes up by 2, which means the odd numbers, 3, 5, 7, and so forth. And true, 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 true. Oh, there are 4 of them. So now this is interesting because it's kind of, I have to look at every single number to find the ones that are prime. And I don't want to have to do that. I would just like to write a little computer program in Maple that tells me which numbers are prime. So for that, I have to show you how to write a Maple computer program for if, then, else conditional. So actually, I'm just going to write, this is just going to be if then, but you have to really pay attention to this. So here the problem is I have too much output, and I have to look for the ones where I have a true, meaning the numbers are prime. So I'm going to modify this program as follows. So instead of, as you go from 1043 to 10,089 by 2s, I want to say the following. If it's in boldface, anything in boldface is a special word in Maple, can only be used in a program, can't be used anywhere else. If is prime n, then. So this is prime is a function which is, it takes on the values true or false. Those are the only values it can take on. So this says if it is a true statement that n is prime, then I want to write out n is prime. So I want to write, let's see, let me try print. I'm not sure this is the right command. Print n. And then I have to end my if section with an end if. So just the way this do loop for and from one thing to another do and then end do, the if something, if this is true, then print n. Let's see what happens. Fantastic. It worked perfectly. So I just looked at all the odd numbers from here to here, and if n was prime, I printed it out. That's pretty good. So this is the if-then conditional. And there's a more a refined form where this says if it's true that this is prime, then you do this. And you could have, in the case that it's not true, then it would do, you would write else. And so in this case, the command would be the following. If this is true, then you do this. If this is false, that means else, or otherwise do this. But in this instance, we don't need that. So I'll just erase it. That's pretty nice. Suppose I wanted to find the primes for a larger range. Maybe let's find all the primes from 100,000 to 101,000. Oops. This is a range of 1,000. I want to find all the primes. Oops. I went by 2, so that's not good. That means I'm only looking at even numbers. Make this 1,001. Ah. There are a lot of them. In that interval of length 1,000, there are this many. Suppose I want to know how many there are. Then I want to modify this program so I count them. So what's a way to do that? I need to introduce a counting variable. So it can be anything. I'll call it L. And I'll start out by giving L the value 0. L equals 0. And now, this is what I want to do. As I go from 100,001 to 101,000, if n is prime, then I print out n. And also, I add 1 to L. The way you do that in Maple is this says, let L be equal to the previous value of L plus 1. And when I'm done, let's print L. Let's see what happens. Ah, so here, as I go from 100,001 to 101,000, I've listed all the primes. I started with L equals 0. If I don't want to see that on the screen, I could end this with a colon instead of a semicolon. And now, here are all the primes listed out, and there are how many? 81 of them. In fact, if I didn't want to know what they were, but just how many there were, I could have simplified the program and skipped the print n. This just means as I run from this number to this number, every time I have a prime n, I add it to L. So now, that's it. This says that there are 81 primes from here to here. If I really want to get excited about this, maybe from 1,000,001 to 1,001,000, yeah, make a bigger range, 2,000. So 2,000 numbers starting at 1,000,000. How many primes are there? Ah, well, that's fast, 152. I can list them out if I want, but in that interval of length 2,000, there are 152 primes. Right? So this is very important. This is, let me just say, you just learned how to program in Maple. That's pretty nice. Let's do one more problem. So this is, everything we're doing is still Calculus 1 review. Okay. So suppose I take the following function. X goes to x to the fourth minus 12 x cubed minus 46 x squared plus 12 x plus 45. What does the graph of this look like? Let's plot f of x. Now it's x to the fourth. That means it has to come around and start to go up. So maybe I'll plot this from x equal minus 5 to 20. Let's just see what happens out there. Then it goes up. So maybe not up so far, maybe to, I'll just do it to 16. So this curve comes down, up, down, up. It crosses the x-axis in 4 places. We know how to find where it crosses the x-axis. That's just solving the equation f of x equals 0. Let's find the local maxima and minima. So what do they teach you in Calc 1? You have a minimum where the derivative is 0. What is the derivative of the function f of x? Minimum and maximum equals 0. Oops, no. What is the derivative? That's the derivative. So to find where you have a local max or minimum, let's solve the equation. Derivative of f of x equals 0. Solve for x. So we have 3 points where the derivative is 0. Minus 2, that's going to be around there. 0.1 is about up there. 11's out here. Let's just look at this right in this range, maybe, just to get a better idea. Yeah, so minus 2 is around there. That looks like it's going to be a minimum. 0.1, that looks like it's going to be a maximum. And the one way out at 11 looked like it was going to be a minimum. How can we tell? Take the second derivative. How do we take the second derivative? Let's say d at 2 of f. That's the second derivative. So let me give these points names. I'll call them, no. Suppose let C be equal to this. Oops. So when I asked, so this is, where was the first derivative? First derivative, oh, I didn't, yeah. Oops. Let me put this in here just so we can see. What is the derivative of f at x? It's a cubic, right? F itself is a polynomial of degree 4. This is a polynomial of degree 3. So it should have 3 roots, and it does. And this is the second derivative. Before I do that, let me take this out. So this is the derivative. And these are its roots. Let me call them C. That's what I was doing. C equals. So what does this mean? It means the way you write a subscript in Maple is square brackets. So C1, that's the first number. C square brackets 2, that's the second number. C square brackets 3, that's the third number. What did you learn in calculus about local minima and maxima? If the first derivative is 0 and the second derivative is positive, you have a local maximum. So you have a local minimum. If the first derivative is 0 and the second derivative is negative, you have a local maximum. So let's take the second derivative. Oops. Where's the second derivative? D at 2, that means take the second derivative of f. It's that function. So if I evaluate this function at C1, that's positive. So that tells us that x equal C1, right there. Positive means is a local minimum. Let's evaluate the second derivative at C2. It's negative. So that means that x equal C2 is a local maximum. Let's evaluate this at C3. Positive. That means x equals C3 is a local minimum. And that's what you have. This is the curve. It comes down, local minimum, local maximum. Let's go out to where we need to be, maybe 16. Yeah. Local minimum, local max, local min. Let's see, here the curve is convex up, then it's convex down, then it's convex up. So how do we find where f of x is convex up and convex down, and find the inflection points? Well, you get that from the second derivative. So the inflection points, at an inflection point, the second derivative is certainly 0. So let's do f solve. Where is the second derivative equal to 0? Yeah, that's right. -1 and 7. So here at -1, the curve changes from concave up to concave down. And here at -7, the curve changes from concave down to concave up. So this is basic calculus 1 with the help of Maple. Pretty good. And the next homework will involve commands that we learned here today. So let me save this worksheet. This is Math 156, Lesson 4. Yep, okay, good. And that is it for today.